Good morning. My name is Andrés Paz. I'm here with Chris Grenath. We both work on the Microsoft Quantum Development Kit, which is the set of tools provided by Microsoft to help developers build quantum programs. Quantum programs are very different from classical programs. On a classical program, you have your ones and zeros, and then you have your Boolean logic to explain how that information that you have stored in those ones and zeros changes from step to step. On a quantum program, you also still have ones and zeros, but the main difference is that instead of just having ones and zeros, you can actually tweak the probabilities of getting a 1 and a 0. So at any point in the stage of the execution, you can tweak the program to tell it that you have a 50-50% chance of 1 and zeros, or any number. Moreover, the way you change those probabilities is by leveraging quantum mechanics, and therefore the quantum name. So on every step, you actually change these probabilities using some quantum mechanics principles. So the point of all this is not to say that quantum programs are hard or that you have to use quantum mechanics, because they're not necessarily that hard. Depends on the algorithm, the same thing as in a classical program. The point is that they're very different. So you don't take just your classical program and execute it on a quantum computer and expect that because it runs on parallel uses probability will actually run faster. You actually have to design programs that leverage these probabilities and leverage these quantum mechanics to do the things differently, take the less number of steps, and therefore run faster. So with this in mind, thank you. We don't expect a quantum computer to actually replace a classical computer. The way we actually think about this is that you have your quantum programs that can be executed on this quantum processor, on this quantum computer. But you still have your classical code, your classical applications that will do what is more efficiently to do on the classical program are most likely to be your entry points, and delegate the execution of a quantum algorithm or of a quantum program into a quantum processing unit. On the quantum development kit that we have released, the way you write your quantum programs is in its own language. We have created a language from the ground up called, obviously, Q#, to help you write these programs that will execute on the quantum processor. As part of the quantum development kit, you start your execution on a classical program, and then at runtime, you load your Q# operation and indicate what target machine you want to run this on. So nowadays, you can execute your Q# operations on a quantum simulator that runs on your classical, on your own desktop. You can run these Q# operations on Azure, or you can also run them on other things like a resource estimator, where instead of executing the entire program, we'll just calculate how many actual quantum resources, how many qubits, how many operations it will take if you want to execute that program on an actual computer. In the future, you will be able to target a quantum processing unit that is running on your desktop, for example, or you could target a quantum machine that is running on Azure, or you can target other different type of quantum simulators. When we launched the Quantum Development Kit about a year ago, you could only write your classical portions, the classical parts of the program on C# or .NET Core languages, F#, Visual Basic, and such. But as we have evolved over time, now we give you more flexibility, and more specifically, we have been working on let you compile and simulate these Q# operations on both Jupyter and Python. Jupyter, for those who are not familiar, is a framework that allows you to build interactive notebooks. So you can actually execute these notebooks on a browser, and within the notebook, you can define cells of code that you can modify there on the spot and execute on the spot directly on your browser. Out of the box, Jupyter came with integration with Python, which is how it was written, but they provided the hooks to add your own languages. So there has been integration kernels created for C#, for R, for F#, and now we are providing an integration, a kernel for Q#. This integration allows you then to write your Q# operations directly on the browser and execute and simulate it directly on the browser without having to write C# code. So your classical portion is still on Jupyter, and now you can just focus on write your quantum operations on Jupyter directly. Again, on top of Jupyter, we have also built integration to run this on Python. And from Python, you load your Q# operation, and then it's very easy to ask it to simulate that operation, passing the parameters it requires. With that in mind, I'm going to now ask Chris to take over and show you the actual code running on Python and how that works.
All right, well, thank you very much. So by way of an example of showing some of the technologies that Andres mentioned, let's start with quantum teleportation. It's a little bit of a whimsical name, as many things in quantum computing are, but points to a really useful way to move data around a quantum computer. So here I've got just a standard Jupyter Notebook interface with a couple different notebooks, including teleportation here as a Q# notebook. So you can tell by the logo in the upper right-hand corner that this is a Q# notebook rather than a Python notebook. And I can write my code out here. So for instance, I'll take a stab at writing out a teleportation algorithm. At the moment, it'll feel a little bit like assembly, but when I run it using Shift-Enter, the IQ# kernel will compile that quantum operation to something that we can then send to a target machine. I can use, and I get down at the bottom a message saying that that operation was successfully compiled and it's ready to go. But as I look at this, maybe I don't understand quite how this works because I see this mResetZ thing that isn't really clear to me. So I can use Jupyter Notebook features like documentation to get a summary of what that operation does right there to remind me so I can help understand. Once I'm ready, I can then run an operation on one of the target machines that you saw earlier, such as the quantum simulator. And here I get out the output returned by that quantum program running just on my Surface Go here, a simulation of how that would act on actual ideal quantum hardware. I can go a little bit further and write things out in multiple cells, using that to isolate and understand each different piece as I go along. I can use things from the libraries provided with the quantum development kit. For instance, the mResetZ operation you saw earlier is one of the things offered by the Microsoft.quantum.measurement namespace. And I can have operations that call each other and build up more complex programs and understand them this way using the Jupyter Notebook interface. Doing this, I can then allows me to focus on and describe the algorithm that I'm trying to understand, in this case, teleportation, and run finally my take two of it here at the bottom using another simulate command to the IQ# notebook. So, all right, let's do this once more with feeling, and now let's do something a little bit more fun. It's so fun I even had to include an emoji for it, but and teleport now arbitrary kinds of states by using features of Q#, such as passing around. You can pass operations to other operations as first-class values, and so this lets me write out quantum algorithms in a really compact way that makes it still easy to read and break down and understand. And when I run that, I get that all of the unit tests here that I wrote out work correctly, and I get the message back that says it worked correctly. We can also do this from Python. So as you heard a moment ago, So what we just saw was using Q# on its own in a notebook, but we can also mix with other kinds of more conventional classical programming, such as using an IPython notebook from within Jupyter. So doing this as well now, we can import the Q# package, and this will give us access to things like allowing us to compile operations on the fly and save them into Python objects, which we can then use the simulate method on to do so, in a very similar fashion, send them to target machines for execution. So it'll take just, and so we again get the same message back telling us that it worked correctly. And doing that, I can also get access to other target machines, such as the resources estimator, which gives me a breakdown of what gates and operations I needed to use to run that, so that as I scale up an algorithm to look at larger and larger instances, beyond what I can simulate locally on, say, a Surface Go, I understand what resources would be required to run that on actual quantum hardware. You can also import operations that you've written in Q# into Python rather than just having to compile everything on the fly. So there's a lot of different ways of exploring and using Q# from Jupyter as a platform. But one of the things that's really cool is how easy it is to get up and running with all of this using the open source technologies provided with .NET Core. You can run 2 commands to add IQ# as a kernel to your existing Jupyter environment. And that provides everything that, that you need to get in and explore and get started with. Please, if you're interested, check out the documentation. We've got an online version of this that you can try without installing anything. And there's a growing community around that we invite you to take a part in. So thank you very much.
We are on a booth on the app sections. If anyone has questions and would like to follow up with us, anything, please come by and let us know. Thank you.